Three.
Hi, I'm Ryan.
I am Ahmad.
I'm Carson.
I'm Yaonan.
This is our ME 3503 final project. For this project, we chose to design our aircraft based on the Cessna Skyhawk. It's a smaller four-person aircraft, including the passenger, so not many people will be on this aircraft. To start off, we needed to get some information so we could do our calculations about this type of aircraft. Its maximum takeoff weight was about 1,150 kilograms. The weight of fuel, 144 kilograms. The weight of the wings and the frame, 762 kilograms. And it has a useful load, which is the weight available for passengers and their baggage, of right around 400 kilograms. The maximum cruise speed is 230 kilometers per hour. The maximum altitude allowable is 4,267 meters. And we're going to use a takeoff speed of about 111 kilometers per hour.
So for the airfoil selection, that was one of the most important decisions that we have to take in order to design our aircraft. Having more researches and resources into the internet, we found that there are some possible modified NACA's airfoil that we can take in consideration. We tried to compare the 4 and 5 digits airfoils of NACA to our aircraft and see what actually works best with the design that we have. The best choice for our design aircraft was NACA 2412, which has the very high maximum CL over CD ratio, as well as it's the most common widely spread airfoil type of aircraft selected for this specific design, which is Cessna Skyhawk.
Once we had our airfoil selected, we needed to go forward to design the wings. We decided to go with an aspect ratio close to the original Cessna Skyhawk, so as you can see, around 7.48. Once we had that, we used other initial values of vertical acceleration, which is standard of 1.5 meters per second squared, the air density at sea level, and the air density at the altitude of 4,000 meters, which is about the maximum for the Cessna Skyhawk. And then we use the aspect ratio formula, which you'll see in the next slide. So once we had all those initial values set up, we needed to go about to find the planform area required to get that amount of lift required for that set vertical acceleration. So to find that, we use the Newton's second law equation that we arranged, as you can see there. Once we had that, we used the lift force equation that we rearranged to solve for the planform area, as you can see there. Then once we found that planform area, we used the aspect ratio formula to solve for the wingspan. Go to the next slide. So that got us, for the takeoff, a total wingspan of around 12.7979 meters, a chord length of 1.71 meters, and an aspect ratio, as we said, close to, if not the same as the original Cessna Skyhawk. Once we found that, we continued to find the angle of attack necessary for cruising, which that was around, I believe, 2.5 degrees. Sorry, 3.5 degrees.
Based on the information we get from previous steps, we find the coefficient of drag at angle of attack, which is 7.5 degrees, is 0.03 at takeoff, and the coefficient of drag at angle of attack, which is 3.5 degrees, is 0.035 at cruising. And follow this drag formula, we can find our drag force at takeoff is almost 400 Newton. When it is cruising, the drag force should be around 1,300 Newton. For induced drag, it is generated by lift force. After air passes the wings, it will turn down a little bit, which makes the straight lift force turn back a little bit and some part become to the drag. According to a research, induced drag will be more than 50% of total drag during taking off. It can even reach 70%. It will about 40% of total drag when it is cruising. Based on this information, we can take induced drag into consideration and find the new drag force for taking off and cruising. It will be about 1,000 Newton at taking off and 2,135 Newton at cruising.
For power and propulsion, we use the formula shown above, and we use the power at takeoff was calculated to be around 30 kilowatts, and the power at cruising was about 136 kilowatts. For propulsion, we used a horizontally opposed piston aircraft engine with a heat efficiency of 25%. The gasoline heat value was 45 megajoules per kilogram, and the density of aviation fuel is about 720 grams per liter at 15 degrees C. Those got us a fuel consumption of about 0.22 liters per minute of fuel at a takeoff speed of 111 kilometers per hour. And then at cruising speed of 230 kilometers per hour, our fuel consumption is 26.36 liters of fuel for every 100 kilometers traveled.
And what we learned in this project experiment is that we found some little bit difference between when plane is taking off and when plane is actually cruising. So as we learned from the previous slides, that velocity at taking off was 111 kilometer per hour, and that gives us drag force of 981, which will actually lead in an actual takeoff power of 30 kilowatt, as we learned in the previous slide. But for cruising, we had a velocity at 230 kilometer per hour, as well as a drag force of 2,135 Newton, which will give us a 136 kilowatt of power needed for that plane in cruising. Knowing that gives us some conclusion for our experiment that we are actually very satisfied with our values. So the power at cruising was much higher than taking off, which was not kindly expected, but from what we seen in the internet and what we had from our resources throughout the Cessna Skyhawk designs, our values seems pretty much made sense to us because it matched like what is most commonly used for this specific design. And thank you very much. That was Mechanical Engineering 3503 Fluid Mechanics project for the final semester of spring 2019, and that's our reference.